I gotta start recording this because I said I was gonna do that. So yeah, so just a heads up, I am gonna record this session and try and upload it probably to YouTube or something, just so that you guys have access to this and so that people who can't show up today aren't gypped out of SI. So it seems like most of you guys are done. I'm gonna give you guys just one more minute for the sake of not leaving anyone behind. But it does seem like D is a very popular answer. All right, let's pull up the iPad. Okay, so hopefully this goes well. All right, we're on number 3 right now. So what we're gonna do is draw a picture. Always a good idea to start with. Let's see if we can't figure out if it's D or not. Everyone thinks it's D. So I'm not gonna ruin the suspense by telling you if it's right or wrong yet. So drawing a picture, always a good idea. Label things with variables first. That's what I'm gonna do. So I've got this bullet, this little bullet right here with a mass of little m hitting this block of mass big M. So this is our initial state, and then after it hits, it's going to turn into this sort of situation where it has a block of big M plus little m moving with the velocity. And let me relabel this as VI, and then this is a VF right here. Okay, so how do we approach this? It's just a nice, simple conservation of momentum problem. So the way we know it's a conservation of momentum problem is because we don't have any outside forces acting on these two blocks, and it's asking for, and a collision is happening. So no outside forces means that momentum is conserved, and the fact that it's a collision means that's an indicator that we use momentum. So that means that PI is equal to PF. So let's write down the definition of what momentum is. So initial momentum, this block right here has no momentum because it's not moving. So we're going to implicitly say that it's 0. So little m times VI is going to be equal to our final momentum. Well, it's going to be both of the sum of these two masses times VF. So that's not an upside down A. That's VF. Okay, so we're trying to figure out what VF is. We just divide this term, the m plus m, over. We get m divided by big M plus little m by VI is equal to VF. And then we can plug in numbers. So I'm not going to bother doing that. The answer ends up being 0.599, which is answer D. So D is correct. Yeah, so we round that up to D. That is not 6. That should be a 9. Okay, any questions on that? We seem pretty comfortable with that. So yeah, I think we're good. On to the next one. This one is a bit more challenging. We've got a projectile and it's fired into the air, and then at the top of its trajectory, it breaks apart. And we know what we know some information about the mass and velocity of one of the parts that it's broken into. And the question is asking about what is the velocity of the other part. Does anyone know what the score of the Packer game is right now?
(28-14) Minnesota, 3:42 left in the fourth quarter.
Damn it. It's not looking good. See, I'm from Minnesota, but I'm a Packers fan, so. Enjoy it while you can, you Vikings fans. We all know you can't win the Super Bowl.
So I'm a bit stuck. I'm just a little bit, the only thing I'm a little bit like iffy on is like what's the deal with like the I with the caret over it and the J
Oh,
with the carets over it? Like what do those mean?
I hat just means pointing in the X direction, and then J hat means pointing in the Y direction.
Oh, cool. Okay.
Yeah.
So, yeah, all right. That makes sense.
Yeah, and it's terrible notation. I hate it. I'm in E&M class right now, Physics 364, and it's we use X hat, Y hat, and Z hat because that's far better notation. Um, okay, so it seems like the consensus is A, but people are still working on it. So I'll give you guys like 2 minutes or more or so, depending on how many more answers I get. Oh, while everyone is still here, and while I'm recording, I messed up the announcement. So I've said this like four times now, but just to reiterate, I messed up on the Canvas announcement. This week's sessions, so there's still no session on Thursday. That is still the case, but Wednesday's session should be at 6:30, not at 5:10.
And then we went to
So hopefully
department.
that makes sense. Monday's session is correct though. That should be it. That's the moral is Monday's session is the time it would usually be along with Wednesday, and then Thursday is canceled. Okay. I think I've gotten enough answers. Are we okay if I go through this one? Okay. So let me pull up the iPad again. So most of us think it's A. I think I got one answer for C, but nearly everyone else said A. So let's see if we can confirm or deny that. So this is problem 4. All right, so always a good idea. Let's draw a picture. So we've got a projectile, and then at the top of its trajectory, it breaks apart. So let's see if we can't sketch that out. We got trajectory. That's a terrible looking parabola, but it gets the job done. And then right here, it's got a velocity given. I'm going to call it v naught. And then I'm also going to label that it has a mass of ma plus mb. That's a b. Close enough. And then I'm going to draw a second picture. So this is before it breaks apart, and then like the instant after this, then it breaks apart, right? So we're really only concerned about the case where about the instant after this breaking apart happens, and then we're gonna dissect that motion a little bit. So really, the fact that this is a projectile is unimportant. The fact that it's in the air is just kind of trying to throw you off the right answer. But in any case, we're going to draw a picture. We've got two parts. We've got MB right here, and that's got a velocity going up. And then we have MA, and that's got a velocity pointing downwards like this. So we know what the components of this velocity are for MA. That's given in the problem. So I'm going to label them generically as Vy and Vx. And then we're asked about what the heck is each component for this vector right here. Okay, so Lauren thinks it's A too. So everyone thinks it's A. So now we just have to dissect this motion a little bit. I did this very rigorously on my paper, but let's see if I can't be a little bit more clearer with this. So at the top of our trajectory right here, we see that our vector, this vector is pointing completely horizontally, right? So if MA, the instant after it breaks apart, if the mass of A has some downward component of its velocity, then more accurately, if it has a downward component of momentum, then mass B must have an equal amount of momentum pointing upwards, right? Because if we start with 0 momentum in the y direction, if our vector is pointing like this, then our vector after they break apart must also point like this, because momentum is conserved when you're sitting in the air and break apart. All the forces are internal to your system. Okay, so that means that Vy is going to be the exact same for MB, or not Vy, the momentum. So we need to be a little bit careful because mass of B is different than mass of A. So if we do the math, that's just, the momentum in the y direction for A is just Ma times Vy, and that's going to be equal to the momentum in the y direction for B, which is just Mb, times, we're going to call this velocity Vby, comma y. So we want to solve for Vby, so you just divide by mass B. Ma divided by Mb times Vy is equal to Vby. So we can plug numbers into this formula. We end up with a value of 33.3 reoccurring meters per second. So that's that. And then we do the same process for the x direction. So we know what our initial velocity is. So momentum in going that way is going to be equal to the momentum going in the other direction. But we need to be a bit more careful because now we're using the case before we broke apart, because that's important. So our equation is going to turn into Ma plus Mb times V naught is equal to Ma Vx plus Mb times the velocity we're trying to solve for, so we'll call that Vbx. Okay, so we're going to subtract this over, and we're going to get Ma plus Mb times V naught minus Ma Vx is equal to MB, so I'll just divide over that MB right now. So MB times VB comma X is equal to our velocity here. So you can plug numbers into this formula. It's a lot more ugly than the other one, but this is general. There's a reason why I'm doing these all with variables beforehand. It's because, well, we can see the relationships between everything. If we make MA really big, we see MB is going to go, VBX is going to go way down, right? Or if we increase V naught, that's just going to make VBX bigger, things like that. So when you plug in numbers, you end up with 56.6 repeating equal to VB. Next. Okay, so if we look at our options here, the answer for that, it ends up being A. So A is the correct answer here. So good job, everyone got it. If you finished, so good job. And if not, that's okay. So go back to this. Okay. More momentum, lots of momentum at the beginning of this test. We got two balls, two pool balls, and they collide and ricochet off each other. Well, they want to know what the final velocity of B is. I think I'll give you guys until about 3, and then we'll see. Come back together. All right, people seem unsure, but mostly think it's B. B sounds good. Okay. I'll just wait until the clock hits 3 and then we'll go over it. So good advice for studying for this class is that do the old exams because they're very good indicators of what's going to be on the test. But as you go further back, the tests get harder. So keep that in mind. If you're trying to really study and ace this test, then do the practice exams because you have plenty of them along with all the solutions, like worked out solutions and everything. So work on them, but recognize that as you go further back, the questions get a lot harder. Yeah, I think they might be making the exams a bit harder because they have no way to prevent you guys from really cheating. So they might be making these exams harder. I don't know because I don't get to talk to Dr. Canfield or Liz Nat about that, but yeah. Okay, so number 5, everyone who gave an answer said it was B, so let's see if that's correct. I'm going to start by drawing a picture. In this case, that might not be necessary, but we're going to do it anyways. So we got that, and then eventually we end up with this sort of situation. I worked this out all algebraically. I'm going to try and be a little bit more clear because I think that just kind of distracts from this situation. So both of these have mass m, right? So we got one billiard ball that goes, collides with another, and ricochets off at an angle. So this is basically the same scenario as before, but instead of two different pieces with different masses, we just need to know we have the same pieces with the same mass. And yeah, so how do we start? Let's do the y direction again. So just like before, momentum in the y direction from this ball is going to be the same as the momentum same but opposite as the momentum in this direction, right? Because those two vectors have to add up to 0. So what we're going to do is say, well, we know what this is given to us. That velocity is we're going to call it, or we know what the top one is, I think. Let me check. Yeah, so we know what the top velocity is. We'll call it Vy. We'll call this y because we want to solve for it. That's a y. Now we're going to do the same thing in the next direction. So pretty standard stuff. M Vy is equal to m times y. We're trying to solve for y. Well, those m's can cancel out, so Vy is equal to y. So both of the velocities in the y direction are the same. And then if we want to do the same thing for x, we say m v naught equals m vx plus mx, where x is this component of our triangle here. So we want to solve for x. We can already cancel out all these m's, and we just get v naught minus vx is equal to x. So we know that both of these numbers are 2, right? Because this is they tell us that this is 2 and this is 2. So if we want to figure out what the magnitude of this this vector right here is, then it's going to be square root of 2 plus 2, or sorry, 4 plus 4. This is Pythagorean theorem. 2 squared plus 2 squared, which is equal to 2 times the square root of 2, or 2.8, which is B. Yep, so you guys all got it right. Maybe I should try picking up pace a little bit more. I'm not sure. Okay, so that's that problem. Now we move on to something a little bit more interesting. We've got a uniform disk with a certain radius. It's spinning, and then we drop a huge mass of putty on it, and it sticks to this thing. We want to know what the final angular speed is of this system in radians per second. Someone asks if the mass of the putty is a point mass, and the answer to that is yes. Man, you guys are going fast. Last exam review, like we only got through like 10 questions. We're already on number 6. We still have an hour left. Oh, 54 minutes left.
Uh, I don't know. Can you like help get started or something?
Yeah, sure. So do you have any ideas on like what equations to use?
I mean, something with a circular motion is what it's got to be, right? 'Cause it's got the
Actually,
whole angular stuff.
um, so no, actually, I think the short answer to that is no. You actually don't need to use anything about circular motion for this. Instead, change your perspective to think about something important is conserved here. So the last problems we've been doing have been linear momentum. This problem
Sure.
we've got, we're conserving angular momentum.
Okay. I think I could figure that. That could make sense, but another thing that's confusing to me is where does the radiuses fit in? 'Cause-
When you're using your equations for that describes angular a thing's angular momentum, then the radius factors into that.
Really?
Yes.
Okay. Okie dokie. I'm gonna try and figure it out then.
Okay. Someone else thinks it's C. I realized I forgot to share computer sound. Like I've got a playlist playing right here, so it's my SI playlist. You guys can't hear it.
42 seconds left in the Packers-Vikings game. Green Bay has the football back behind by 6 points.
Oh shoot! Really? That's exciting. Oh man.
They're at their own 35-yard line now, 37 seconds left.
Oh, dang! I wish I could see. I believe. I remember freshman. So I'll give you guys like one more minute. I don't want to spend too much time on this problem, but I'm gonna tell the story while I wait. And it was freshman year for me, so that was 3 years ago. I'm a junior, yeah. So technically it's 3. 3 years ago, I was in the dorms, and it was Packers v Bears. It was like the first game of the season. It was the most exciting game I think I've ever watched. And I didn't even watch it. I watched like the last 30 seconds. The Packers were behind like the whole time, and then there's one play. I think it was like they returned to kickoff for like the full game. And the whole dorm went crazy. It was just everyone was shouting in the halls the whole time. And then people were shouting out the windows, like either very upset or very happy. I was one of the very happy people. It's just a very fun time. One of the most fond memories I have of freshman year. Okay, so how are people doing on this? Do we want more time, or are we have we hit a point at which we're mostly stuck?
Yeah, I'm a little stuck.
All right, that's fine. Yeah, you're definitely not alone in that. So let's, I'll pull up the iPad. Okay, so in this problem, let's start by sketching out what's happening right after I write down the number. So number 6, we've got a rotating disc. That's, oh, let me pull up the pen. We've got a rotating disc, and then we drop a little bit of mass on it. So let's label things a little bit. So this is a mass of big M. It's rotating at a rate of omega. Okay, and then we're going to drop a mass on it. That mass is going to stick, and that mass sits at a point that is halfway away from the center. So if we drop a point mass right there, distance, let me label the radius right here, r. This distance right here is going to be r over 2. Right, because the radius is 1 meter, and then we drop the mass at 0.5 meters. Okay, so it's still rotating, but this is going to be rotating at a rate of omega 2. So let's label things. This is omega 1. This should be omega 2. Okay, so this is a conservation of angular momentum problem. In case that wasn't obvious, the way we know that is because, well, we've got something rotating, right? So it's rotating, it is not moving side to side. That means that we have, it has some kinetic energy, but all that kinetic energy is stored in spinning, not moving it side to side or anything, which is slightly different. So we have a different set of equations that describes that kind of movement. And we know it's a momentum problem because we've got some initial condition and then we like drop something on it. There's a sort of collision that happens, and then that changes the situation. So now we can throw some equations at this. So we're gonna, if this is an angular momentum problem, then we're gonna use this quantity called L, which just stands for angular momentum. So what I'm gonna say is Li is equal to Lf, right? Because angular momentum is conserved. There's no forces that are acting tangentially from this lump of putty as we drop it down, and that's why angular momentum is conserved. Yeah, all the forces are symmetric. They all point towards or away from the center of rotation. So let's write down what the definition of angular momentum is. There's 2 ways we can write it. It's either r cross p or it's I omega. In this case, it's more useful to say I omega. So let me move that down a little bit. Let's say I omega. And to be clear, I'll say omega 1 is equal to I2 omega 2. So the reason we're allowed to do this is because, well, or no, the reason we're labeling these, right, is because this I1 is a different value than I2. And we're looking, and we know that the omega changes, right? Because if omega didn't change, it would be a very interesting problem. And that wouldn't make any sense either, right? Because when you drop something on it, it seems like it should slow down. Because it's got more mass to be accelerating. So if we're looking for omega 2, it's a good idea to divide over that I1. So I1 divided by I2 is equal to omega 1 is equal to omega 2. Okay, so we've got this formula. Now we just need to slot in what I1 and I2 are. So I1, well, what's spinning here? I1, we've just got this disk. So we know how to describe a disk spinning. If you look at your equation sheet, it's a cylinder or a disk. I don't remember which one it's called. But the moment of inertia for that object is 1/2 m, and I'm going to use big M because we need to describe different mass than this little m right here. So big M times big R squared, that's what I1 is, and then we're going to divide by our new moment of inertia. So there's one very important property of moments of inertia, and that's that they add together well. So if you have one object and then you like stick it on another object, then you have new object, right? And the new object is the assembly of those 2 new objects, but the moment of inertia of it is just the moment of inertia of the first object plus the moment of inertia of the second object. So we still have the cylinder here, 1/2 big M r squared. But now we have this point mass at a radius of r/2 away from the center. Well, the moment of inertia of a point mass is just m times r/2 squared. It's the radius. It's m times the radius from rotation. Okay. So now we just have to do a bit of math here. We can factor out an r squared from both of these, so that's going to cancel out right there. We're going to flip 1/2 over, so this 1/2 is going to go away. We're just going to skip a few steps. We get it m/2. Let me double check if that's right. Yep, that's right. Omega-1 is equal to omega-2. And then we can plug in all these numbers because we know what each one of these are, and we're looking for omega-2 here. So we know what all these are, and when we plug in the numbers, we get omega-2 is equal to 5/6 pi. Which is, let me check, that's answer C. Cool. All right. So, we didn't talk about angular momentum a lot, and it's a surprisingly useful concept. So if you were confused by this, that's okay. It was kind of brushed over. I don't remember Canfield talking about it a lot, but the process for any angular momentum problem is usually very similar to this. You have a scenario before, a scenario after, you determine, well, is angular momentum conserved? Usually it is. And if it is, then you can just do a very similar procedure as right here. Okay, any questions on that? Someone asked, what is m r/2 squared? That quantity I plugged in on the bottom of my fraction. That's the moment of inertia due to the lump of putty that we dropped. So it's r/2 because that's how far away we are from the end of the disk. That's 0.5. Yeah, so that's what that represents.
And did you get that other moment of inertia just by using the one thing off the like I plus I thing?
Nope, you don't have to use the parallel axis theorem for this because you know the I for a solid cylinder. Well, a solid cylinder is just a disk, right? It doesn't matter how thin or thick that thing is. I for a solid cylinder is just 1/2 mr squared. So that's where I got it.
Ah, sick.
Yeah. Okay. So number 7 is a dumb problem, and we're going to skip it and come back to it later this week. I don't know why they decided to put it on the test. It's a mean problem, really stupid. We're going to ignore it. Yeah, I hate that problem. So we're going to do number 8 instead. But we will come back to number 7 later this week, on either tomorrow or on Wednesday. But keeping with the things spinning theme, we've got a wheel with a hoop and 3 spokes. So we just want to describe the angular acceleration of the wheel due to this torque. Did anything interesting happen with the Packers game? Is it still happening? Gotta know. Oh my God. That's a feels bad man moment right there. What a way to end it. 6 points down, 30 seconds left, and you fumble? Come on. Unacceptable. Well, can't win them all. I have a very long night ahead of me, guys. I'm going to have to work on my PDE's assignment. Anyone who's considering, well, I don't know what it's like for engineers. I don't know if that's a required math class, but for physics major, partial differential equations, it's a required math class. Hardest math class I've ever taken, and I'm going to get a math major. So I've taken a lot of math classes. My God, that class is insane. Okay, 3 people for E. All right, people are starting to get some answers. Awesome. Give you guys like 1 or 2 more minutes, and then we'll go over it. Is anyone stuck on this one? Doesn't know where to start. Okay. If you are stuck, remember the equation that net torque is equal to I alpha. So we know what torque is, and we know what I is by looking at our, like they give us the assembly of things here, and then we can figure out what alpha is from there. Don't be afraid to message me if you're stuck, because I don't want you guys just sitting here waiting for an answer. That's not very useful. That being said, I am going to run through this just so we don't spend too much time on this problem. We have plenty of other pretty similar problems to get through. Yeah, the next one is going to be quite challenging, I think. So we'll go through this one. Yeah. All right. So number 8, not number 7. what do we got? I'm not going to draw a picture since that was given to us in the problem. Actually, no, I'll just redraw it since you guys can't see it. So we got 3 equally spaced. We got a peace sign here. That's what we've got. We know information about each one of these rods that are these rods, and we know about these the hoop here. So we'll say that the hoop has mass m1, and then the rod has a mass of m2, and then this has a length of r, right? Because it's our radius. So the equation we want to apply here is net torque is equal to I times alpha. So we know to use this because we're given a torque and we're given and we know how to figure out I, and we're trying looking for A. So it's got everything we need in it. Okay, so net torque we're not going to worry about right now because that's just a number that we're given. So figuring out what I is kind of the key here. So we're going to use the fact that I adds up nicely. So first things first is we're going to use the fact that we're going to use the parallel axis theorem to figure out what the moment of inertia is for one of these rods. So if we can figure out what the moment of inertia is for one of them, then we'll be in a good, we can just multiply that by 3 because they're all identical. And we'll have accounted for all of them. So to do that, we need to use the parallel axis theorem, right? Because I said we're on your equation sheet, you're only given the fact that the moment of inertia of a rod about its center. And we need to figure that out. So we're going to sketch out this rod. We say this is its center of mass right here. So what we're going to do is say, okay, I sub Cm is equal to 1/12 ml squared. So it has a full length of L, so 0 L right there. Okay, so what we're going to do is apply the parallel axis theorem. So what is the parallel axis theorem? It says that our new moment of inertia is equal to I sub Cm plus m times d squared. So d squared is this distance right here. Because we want to pivot about this point. This is where we're pivoting. So this is our d. So L over 2 in this case. But in general, it's just the distance from the center of mass to your new pivot point. So if you, just to really drive this point home, if you had some irregular shaped object like this, with the center of mass like right here, and we would ask the question, all right, what is the center of mass if I were spinning around a point that's sitting right there? So it's spinning like this. Well, then D would be this distance right here. That would be D. Just so we're extra clear on that. So, okay. So now we just plug in the things. So I'm going to kind of fly through this. So 1/12 ml squared plus as mass of m, and this is L over 2 squared. So you get 1/12 ml squared plus m over 4l squared. So 1/4, you multiply that by 3 to get the common denominator. So you get 4 over 12 ml squared, which equals 1/3 ml squared. So that's our I for the rod, but we're not done yet. Because that's the rod, but we have 3 of them. So we need to multiply that by 3 and then add that to the moment of inertia of the hoop. And then we'll know what the moment of inertia is for the whole rod. Because remember, the whole wheel, rather. Because remember, the whole wheel is made up of all these individual parts, but moments of inertia add together nicely. So now to figure out what I total is, I tot is just going to be moment of inertia due to a hoop. That's given on your equation sheet. And it's actually exactly the same as the moment of inertia for a point. But that's not really the point here. mr squared. So that's the hoop plus 3 times the moment of inertia of each individual rod. So that's 1/3 times m2 times r squared, right? Because each rod has a length of L. So we see immediately that this 3 is going to cancel out to 1/3, and we end up with m1 r squared plus m2 r squared. So we can factor out an r squared from there, and we get m1 plus m2. The whole thing times r squared. So this is our total moment of inertia that we're going to plug into I alpha equals net torque. So that's what we're going to plug in. Now that we know what I is, it's just a matter of dividing, like plugging in numbers now. So alpha is equal to torque. That's a tau, trust me. So there's not much more simplification we can do here with the algebra. M1 plus M2. So plugging in the numbers, you end up with a value of 100, almost exactly, if I remember correctly, which is E. So those of you who did pick E, good job. If not, it was a bit of a complicated problem. You had to apply the parallel axis theorem and then recognize how to combine all these moments of inertia up. But does that make sense to everyone? Okay. Sure seems like it. So we will move on to number 9. This one, I think, is a bit confusing. Hopefully it doesn't mess too many of us up. But what we've got is, so a person is standing on a merry-go-round. Merry-go-round is not moving, and then they have a ball. And then that person throws the ball at a certain velocity, and then they start spinning on that merry-go-round. The question is, what speed do they start rotating? So they would need our answer in radians per second. What is that velocity? That's what we want to figure out. So think carefully about what's happening here, what concepts to use. Let me know if you're stuck, and I'll see if I can't help. All this talking has me very dehydrated. Now that Halloween's over, guys, I'm going to have to start thinking of Thanksgiving icebreakers. Hydrate. That is. What is everyone's favorite Thanksgiving food? I've got to know. Potatoes? Well, okay, but how are they prepared? That's what I want to know. Not even a contest. You don't like any Thanksgiving food. Come on. Not even pie? Jacob, you like the turkey. See, I feel like the turkey is turkey as a food is bland and boring, you know? That's why we have gravy and things, to spice it up, make it better.
That's what the side dishes are for.
Well, sure, but then I don't disagree, but then is turkey really the best part?
Still, yes.
All right.
The other side dishes just make it even better.
All right. I guess I can understand that. Apple pie is the best fall pie. Better than pumpkin, really. Pecan pie. Okay, pecan pie. That is amazing. I had never tried pecan pie until I was like a teenager. And then I went to my aunt's house for Thanksgiving. And I tried it, and I ate like half of a pecan pie all by myself. Because it was so good. Pumpkin is trash tier. Come on. It is delicious. Pecan is S tier. I don't disagree. Pecan pie is amazing. Also, don't let me distract you from doing physics. I do love talking about Thanksgiving food, but do work on the problem, please. even though I totally started this myself. Okay, I'm very surprised no one said gravy, right? Because gravy, that's the best part of Thanksgiving, right? The gravy, you could put it on anything. Mashed potatoes, vegetables, turkey, like literally any savory dish. You put the gravy on and it becomes like twice as good at least. Gravy is the best part of Thanksgiving. Okay, someone thinks it's A. Not a fan. How can you not be a fan of gravy? You see, maybe the problem is that my family. So my mom she's not great at cooking any sort of meat. Like whenever and my dad's a vegan, so the turkey was usually an afterthought at my house. Okay, I will stop talking about Thanksgiving for a second. Someone is stuck. So if you're stuck on where this problem is, I don't blame you. It's a little bit confusing. But I think a good way to approach it is think about angular momentum again. And the reason we think about that is because, well, we don't have any, we just have a nice clean system. There's no forces outside or that are doing any work that cause us to spin other than the person who's throwing the ball, right? If you throw the ball, then that's going to cause you to spin, but that force is still internal. There's a third law pair between the ball and you. And that means that the force is internal to the ball, you, and merry-go-round system, which means angular momentum is conserved. And from there, just say Li is equal to Lf, and then try and expand that out. Write down what each, what each I is and omega and whatnot, and see if you can't solve it from there. But yeah, back to Thanksgiving. See, yeah, my family, no one in my family really enjoys like cooking any sort of meat or anything. Like my sister, she never really learned how. My dad's vegan, so he doesn't care. My mom never really learned how either. So I'm the one who has to cook the Thanksgiving turkey. Isn't the initial L 0 though, because it's at rest? Well, yes, it is. Which means the final L is also 0, but if you account for each, for the directionality of everything, you should be in a things should work out. How do you find the L of the ball? Remember that on your equation sheet, it says that your that L is equal to I omega, but it's also equal to R cross P, or P cross R. I never remember, but it's equal to that, and we know how to figure out what P of the ball is, and we know how far away it is.
Well, what does it mean when something's crossed something?
It's the cross product. So if you don't know how to do that, look at the first page of the equation sheet, and it's got the formula on there.
Cool.
Okay, Tyler thinks it's A as well. Oh, okay. No idea how to approach it. Okay. So I already said that it's an conservation of angular momentum problem, and we also know that our initial angular momentum is 0 because nothing is moving. So the key point here is thinking about how does the ball that has a certain amount of angular momentum after it's thrown, along with the merry-go-round in person after they're thrown. And those interact to add up to 0. So if you can figure out what the angular momentum is of the ball and then the angular momentum of the guy sitting on the system, then you should be able to figure out what omega is for the merry-go-round. P in R cross P is momentum. So, you know, I think it's because something to do with Latin, but, you know, we like being confusing, us physicists. So we name our variables stupidly, like P for momentum and J for impulse. Someone asks, is L the distance from the ball to the center of the circle? And capital L is not. Capital L refers to angular momentum, but the R in R cross P does refer to the distance from the ball to the center of the circle. Okay, another person got A. It seems like some people are either done or still at the beginning of the problem. So I'll give you guys like 3 more minutes just to try and work through something. But at 45, I'll run through the solution, and then we'll have time for probably 2 more problems. And keep in mind that I didn't expect to finish this exam today. That never ever happens, especially since it's just me, and it's online. So the rest of this week, Monday and Wednesday sessions will be going through this exam, almost the exact same format, but without the half an hour explaining equation sheets in the beginning. Was that helpful, the equation sheet thing, or should I stop doing that?
Honestly, it was kind of helpful. I mean, like I definitely think it was more helpful when we got to the problems because you actually got to use them.
Yeah.
But I think it was very helpful just because like the problems would have been a lot harder had we not known what any of the equations were.
Yeah. Yeah. Okay.
And
All right,
maybe
then I
I'm
will-
just behind compared to most people, but I sometimes it's hard for
Hey.
me to keep track of what all the equations do and stuff.
Yeah, it's an overwhelming amount of equations. So I think the reason I do it is because when I first started as an SI leader, that's what like the people who were doing this class before me did, and it seemed like it was helpful then, but it's just really hard to keep the pace up. That's the thing that I'm worried about. Like I spend too much time on
Yeah.
it.
Yeah, I do feel like maybe you could have kept it a little bit briefer, but who knows, right?
Yeah. Okay. Yeah. So generally positive. All right. Good to know. And just a heads up, I do plan on doing a final review for this class, which will be structured very similarly. But I don't know when that's going to be or if I'm going to have time. We'll figure it out, though.
Would you be able to record the sessions on Monday and Wednesday? Because I doubt I'd be able to show up to either of those. in
Yeah,
my
I can do that.
schedule.
Okay, it's 3:45. Are we okay if I run through this? Okay. Yeah, I think we spent quite a bit of time on this one. So this is a challenging problem. If you guys were stuck or struggling with this, that's okay. It's not a super intuitive one to be working on. So what we're going to do here is start by drawing a picture. So this is problem 9. What we're going to do is, okay, well, I didn't even draw a picture in my notebook, but a better idea is to do that. So we've got a merry-go-round, and then we've got a person, not necessarily a male, standing on merry-go-round, and then they throw a ball in this direction. So let's actually make that picture a lot better by making it a top-down view, and we just have a ball that's thrown this way. So this is a radius of r, and the angle between the ball and the radius is 90 degrees. So that's an important point. That's I don't think that, and we know that that it is given. We know that it's 90 degrees because the problem says that the man throws the steel ball tangentially at its velocity. So we know that, and then we also, just to be clear, this little dot here, that's a point mass that we're going to treat as the person who's standing there. Okay, so if we think about this situation, then we know at the beginning we're not rotating, right? So, and we also know that all the forces are internal to our system, so momentum is conserved, specifically angular momentum, because linear momentum isn't conserved, but we're not going to talk about that. Li is equal to Lf. That looks like a J. Let me make that better. Li. Okay, so Li is equal to Lf, but we know we're not spinning in the beginning, so we can't have any angular momentum. So that's equal to 0. So Lf is where everything comes from. All right, so let's consider. We've got two things that are moving in this situation. We've got the ball, and then we've got the merry-go-round. And the guy who's standing on the merry-go-round. We're going to treat the guy in merry-go-round as one system, like they're one thing, because the guy doesn't move around the merry-go-round, so we don't have to worry about any of that. Okay, so that's where the 0 comes out, right? Because if we were to consider just the merry-go-round and ignore the ball, then this equation would not make much sense. Then we would not have a conservation of angular momentum, because we go from 0 to having some, and even though you threw the ball, like it wouldn't make sense because we're not including the ball in the situation. But if we do include the ball, things will make sense. So let's put some math to it. So Lf is equal to I omega, right? So we got to figure out what I is, and we also need to include the angular momentum of the ball, but that is r cross p, right? It is r cross p, not p cross r, correct? I can just check. Yeah, L is r cross p. Okay. So we've got this. This cross product, remember that the magnitude of the cross product is given by the magnitude of each vector times the sine of the angle between them. But we established in the beginning that the angle between the velocity of the ball and the radius, so r, right, because the ball is moving that far away. So this is very confusing, actually. The ball should be sitting right here, because this is the situation where the ball is just after it's been thrown. Yeah, so rp sine theta, that theta is 90 degrees. So that's got to become 1. P is equal to m times v. So we have 0 is equal to I omega. And eventually we want to solve for what omega is. That's where our goal is here. Plus rmv, right? Because this is 1, r times mv is just what r cross p ends up being. So we've got this. Now we're going to solve for omega. But first things first, we got to expand this I a little bit. So we've got a point mass sitting on a cylinder. So we know how to describe the moment of inertia of a cylinder. That's just 1/2 times the mass of the cylinder. That's mass of the merry-go-round, so m times the radius of that thing squared, and then a point mass is just the mass of that thing times its distance from the center, which is r squared. And then we're going to subtract over the rmv right here times omega. So, come on. So all that's left to do is divide over this whole thing to the other side. Yeah, so, and sorry, this r should not be little r, it should be big R, right? Because we're a distance of r away from the center of mass. Yep, so let's just rewrite this. Negative RMV divided by, okay, 1/2 big M R squared. I'm going to drop this subscriptum just, we call it little m R squared is equal to omega. Get rid of these r's, and that's about as simplified as it can get. So m times v, so the momentum of the ball after we throw it. Okay, that's why I didn't do that, so I will fix my notation here. There we go. Yeah, so 1/2 mmr plus mr equals omega. So this is kind of a nasty formula, but it gets the job done. So we plug in numbers to this. We know what every single one of these are. After we do that, we get a value of 0.5 radians per second. So those of you who picked A, that's correct. But the key point here is realizing that we have to include the ball in our system after it's been thrown, because otherwise the angular momentum isn't conserved and things get complicated. So yeah, this is a little tricky. The negative you drop because it just corresponds to it rotating the direction of the rotation. So if the ball is going upwards, then the thing is going to rotate this direction, which I said is negative. And if you want to get rid of it, you could say that it doesn't go anywhere. I also forgot to just include it, so that should be a minus sign right there. Yeah. No, M is the mass of the man. Big M is the mass of the man. And then M sub M is the mass of the merry-go-round. Yeah. Any other questions? Okay, it doesn't seem like it. So we have time for about one more question. Let's do, I think this is number 10 is a good one to end on. Yeah, we've got a 20-gram spherically symmetric ball with radius 10 centimeters, and it gives us the moment of inertia. And it's released from the top of the incline and rolls without slipping down to the bottom. And we want to know what the speed of the mass is at the bottom. So how fast is it moving translationally, not how fast is it rotating? I'm gonna have to upload this video to my school YouTube channel or something. Once the session's over. I actually did that for SI last semester. I did 222, and I did videos explaining how to use the right-hand rule to do something. That's not important. But I did like 2 20-minute videos of it explaining that on the school YouTube channel. So go sub to me. Go sub to my NetID on YouTube. All right, so we got B. I will neither confirm nor deny whether or not that's the right answer. Oh, you know it. Of course. No, I think the only person who's subscribed to my school YouTube channel is my own personal account. If you would like to subscribe to me on YouTube, though, you can. On my personal channel, I upload Tetris videos. Just like it's kind of just like an archive. But I play Tetris. No Pomino. See this thing on the bottom of my screen here? That's my Tetris game. And I upload videos of that. You can see me beat Speed Mania 2, which is not an easy task. Took me like 7 years to beat it, but I did it. And now I can do it semi-consistently. Hey, I've been there, Christian, man. I've played Tetris since I was like a lot, since I was 10 years old. I still that happens to me. See, my first Tetris game was Tetris Worlds, which was the first modern Tetris. So I was brought up on the modern rules. So I wouldn't say I'm good at T-spins and stuff, but I know them. We have 3 minutes, so I don't want to keep you guys too late. Is it okay if I go through this one, even if you guys aren't quite finished? Yeah, okay. All right, so just a refresher, this problem is asking us to figure out what the speed is of a ball at the bottom of an incline. So this is problem 10. We're gonna sketch out this picture. It's pretty simple. In the beginning, we've got a ball at the top, and then at the end, we've got a ball at the bottom, and it's moving. It's at rest at the beginning. So we'll say it's at height h. And that's actually all we need to know. So conservation of energy is what we're gonna apply here. We're gonna say that mgh, right? So we just take a snapshot at the beginning, right? In the beginning of the scenario, we're not moving. All we have is gravitational potential energy. So mgh. And then at the end, we take another snapshot. Well, at the bottom of the incline, we've got both rotational kinetic energy and translational kinetic energy, but we don't have any gravitational potential energy because our height is 0. So we're going to say is equal to 1/2 mv squared plus 1/2 I omega squared. So we've split our kinetic energy between spinning and moving. Okay, so we got to figure out what I is, but well, actually we don't need to figure out what I is because they give us that as just a raw number in our equation. So we just want to figure out what V is, but we got to put omega in terms of V because we roll without slipping. So that's an important condition. And we're going to use the V equals R omega equation. So that means that V divided by R is equal to omega, and then we put omega in terms of R, and then we can plug that in here. So we end up with mgh is equal to 1/2 mv squared plus 1/2 I, and then v divided by R quantity squared. Okay, so we're going to do a little bit of throw a bit of math at this. Start by multiplying that 2 over to the other side. 2mgh, and then we're going to factor out a v squared because that's what we're looking for. We're looking for v, so we want to isolate that variable. So we're going to get m, and we multiplied by 2, so the 1/2s have gone away. So we get m plus I divided by r squared, and this whole thing times v squared. Yeah, that's right. Okay. So we've got that, and then we divide over this, and then we're going to take a square root. So we end up with 2mg times h divided by m plus I divided by r squared, and take the square root of that whole thing. That's going to give us our velocity. And then we know what each one of these numbers are. That's given in the equation. I is just that number given at the beginning. So you can plug the numbers in. You end up with 3.6 meters per second, which I think is B. Yeah, so that the correct answer to this one is B. Look at that, I managed to end on time. All right. Yeah, so thank you guys for showing up. It is 4:01, so officially overtime as usual. But yeah, so thanks for showing up. Again, reminder, Wednesday session should be at 6:30, not at 5:10. So yeah, if you guys could leave your net IDs in the chat before you leave, that would be greatly appreciated, so that I can take attendance, and yeah, that'll be fun. I don't know what the averages are for the last few years, but I do know that they're,
The average on the first exam was a 58%.
yeah. So I think they're a little bit low this year. I think that the average tends to be around like a 70 when it's in person. But I can't say for sure. It's been too long since I've taken this class, and I don't have access to that information. Yes, they do. I do believe they curve this class. So I can't say how much. Usually they curve it about a letter grade, I think. But yes, the class is curved.
Yeah, I can attest to that too, because I have like a grade that's like the percentage shouldn't be possible for the grade that I have. Like,
Yeah,
Yeah.
they have it weighted by 5%, I believe, right now, but then there's probably going to be an extra like 5 to 10% curve if I'd guess right.
I believe so. Yes. Yeah. So, and on the last exam, I think on the final, they usually have questions they like just take off, so that your total grade just goes up by like 2 questions or something. That tends to be the case. So if you're super worried about your grade, try not to worry too much. I know it's hard, but they do curve the class. So long as you're not absolutely bombing it, you should be okay. But please do study. I don't want you guys to fail. Okay. What else? Yeah, sessions on Monday and Wednesday this week, and no session Thursday. If you guys are looking to study, I highly recommend doing practice exams. So that's a good idea. And if you have any questions on how to solve the problem, you can always message me through the SI website, or if you really want to, you can email me through my school email. It's bburdick@IA State. So I'm not supposed to give you guys that, but I don't care. Yeah, I think that's all I've got. So yeah, that's it. Have a good rest of your weekend. I hope that you guys don't stress out too much about this exam. I'm here to help if you are. So